Alright, welcome back. Math 1910. We're in Chapter 3 still. We're moving right along to Section 4. We're going to talk about concavity and how we use the second derivative test. So where last section we talked about using the first derivative test and what that gave us with, critical points, and we could tell whether our function was increasing or decreasing. Now we're going to apply the second derivative test when we go through this and see how that gets us, different ways we can tell concavity and what we calculate to be points of inflection. All right, those are very similar to critical points, only we're doing that test using the second derivative. All right, so let's talk about concavity real quick. So if we look at the definition of concavity, all right, it says let f be differentiable on an open interval I, and the graph of f is concave upward on I when f prime is increasing on the interval and concave downward on I when f is decreasing. So this will make sense when we start looking at graphs of things like, and you're actually able to see the concavity. All right. Sometimes we call it concave and convex. In this particular book, use concave up, concave down when we apply this. Okay. So if we take a look here, it says let f be differentiable on an open interval I. If the graph of f is concave upward on I, then the graph of f lies above all its tangent lines. Okay, so that means the graph is sitting up. We have concave up. All right, so when we talk concave up, I want you to think of ideally just a parabola pointing upwards. If we talk about concave down, think of something like a parabola pointing downwards. Now, it's not always a parabola. It might be just half of that chunk. But I want you to think of, is the graph pointing up or down at these particular points. Okay, so if we analyze it with the down, all right, it says let f be differentiable on an open interval I. If the graph of f is concave downward on I, then the graph of f lies below all of its tangent lines. So that's kind of teaching us how to draw the tangent lines to this as well. All right, so I'm going to step back a slide. So if we look at concavity up, notice if we draw the tangent lines there's 3 in blue. The graph is on top of the tangent lines, where the 3 here with concave down, all right, the graph is actually lying below the tangent line. So that's helping us understand, concavity and its impact. So this one should really nail it kind of down for you guys, okay? If we take a look at this graph here, it's f of x equals 1/3 x cubed minus x. That's the graph that's on top, okay? And if we take a look at, we can physically graph this function and look at the graph of it, and we can tell when it's concave down, when it's concave up. So if we look, all right, at this graph, we can see that from negative infinity all the way to 0, this graph is going to be concave down, right? It looks like it's making a cave. And then it changes, right? At 0 to infinity, it looks like it's going to be concave up. So you can look at the different intervals and what's going on there. Now, the first derivative actually helps us understand this as well. So if you notice on here, the equation is f of x equals 1/3 x cubed minus x. The derivative, f prime of x, is x squared minus 1. That's the bottom graph. So if we show those two on the same kind of graph scenario, you can see, all right, as we're looking at concavity, when the first derivative, okay, if we take a look at what's going on with the first derivative and look at what's going on with the second derivative, there's a couple different things we can look at. So from the last section, if we look at the first derivative, all right, and that's the bottom graph. If we look from negative infinity to negative 1, the first derivative is positive, which tells us the original function is increasing from negative infinity to negative 1. Then what? Okay, we still look at the first derivative. What happens when the first derivative is negative? We can see the first derivative is negative from negative 1 to 1. That tells me the original function on top is decreasing from negative 1 to 1. Okay? And then from 1 to infinity, the first derivative is positive. That original function goes back to increasing. So how does that help us here? Well, we can apply concavity to the first derivative as well. So if we look at the first derivative graph at the bottom, from negative infinity to 0, the first derivative is decreasing. Okay, so as long as the first derivative is decreasing, the original function is concave down. Okay, now let's continue on looking at the graph of the first derivative at the bottom. from 0 to infinity, that first derivative is increasing. So what does that tell us about the original function? Since the first derivative is increasing from 0 to infinity, it tells us that the original function is concave up. So there's how we can use the original function and the derivative to understand when a function is concave up, concave down, and as well as if the original function is increasing or decreasing. So very important that we understand those properties of the first derivative. Okay, now we can do a test for concavity using the second derivative. Okay, so if we look at theorem 3.7, all right, it says let f be a function whose second derivative exists on an open interval I. If the second derivative is greater than 0 for all x and I, then the graph of f is concave upward on I. So we're going to take the second derivative and apply a test, kind of like we did last section. All right, and we're going to do test intervals, and based on if the second derivative is positive or negative there, we're going to be able to conclude whether the graph is concave up or concave down. Because, you know, you're going to be like, hey, Mr. Slady, this is easy. I can just graph this for this function and see if it's concave up or down, or increasing or decreasing. Well, I might not give you the original function. I might give you the first derivative, or I might give you the second derivative and have you tell me everything that you possibly can about the original function. So that's where you got to really understand this, because you can't work backwards unless you got a really good calculator from the second derivative to graph the original function. All right, so that it'll actually, you know, double integrate for you. But anyhow, second part of the theorem 7, right? If the second derivative, if f double prime of x is less than 0, meaning if the derivative is negative there for all x and I, that means the graph is going to be concave down, the graph of the original function. So we're going to test the second derivative that's going to give us information about the original function. So make sure that you understand that. So let's do an example here. We want to determine the open intervals on which this graph is concave up or concave down. All right, so we have f of x equals 6 divided by x squared plus 3. Now the goal is to get to the second derivative, right? There's a couple different ways you can do this. You can either apply the quotient rule, or we can rewrite that denominator with a negative exponent and use the chain rule and product rule and those sort of things. Okay, so we should be able to tell though that this graph is continuous because it's a squared in the denominator. No matter what value we put in for x, this graph will not have an asymptote and not have anything that's not defined. Okay, there's not a value I can put in for x that makes the denominator go into 0. All right, so if we find the second derivative, rewrite the original. So this is just one method. You can use the quotient rule if you want. It doesn't really matter. Somehow do your differentiation however you want to. I'm just showing it rewriting the exponent. All right, so that gives us the first derivative, and then if we differentiate all that piece doing the quotient rule, there's our second derivative. All right, we got to combine some like terms and do some algebra simplification. But our second derivative turns out to be 36 times x squared minus 1 divided by x squared plus 3 quantity cubed. Okay, so, you know, work through, make sure you know how to do the derivative. I'm assuming that you know how to do that. We spent all of chapter 2 doing those kind of derivatives. All right, so now let's apply the second derivative test. So that means the second derivative test is we need to set the second derivative equal to 0. So you're going to say 0 equals 36 times x squared minus 1 divided by x squared plus 3 quantity cubed. Well, when we multiply both sides by x squared plus 3 quantity cubed, we get 0. So then we divide both sides by 36. All right, we still get 0 equals. All right, so we're going to have 0 equals x squared minus 1. Okay, that's what we're solving for. So that's when the second derivative is equal to 0. So when we have 0 equals x squared minus 1, that tells me x squared equals 1. And then I square root both sides, and I get x is plus or minus 1. Those should be deemed our points of inflection that we're going to talk about in a little bit, but those are the points that we're going to base our intervals on. Okay, so we have 2 points now. We have -1 and 1. So we're going to have 3 intervals because we have 2 points, just like we did last chapter, or last section. Okay, so we're going to have an interval from -infinity to -1, from -1 to 1, and from 1 to infinity. Those are going to be our test intervals. And what we're testing for is to see if the second derivative is positive or negative in those intervals. And when it's positive in that interval, that means it's concave up. If it's negative in that interval, we're going to talk about concave down. So you're going to make a chart with those intervals. So if we look at our first test interval, -infinity to -1, we're going to choose a really easy value arbitrarily to plug in or to substitute in. So let's choose x equals -2. If we substitute x equals -2 into the second derivative, remember we're substituting everything now into the second derivative, it ends up being positive. F double prime of -2 is greater than 0, it's positive, so we can conclude on that interval from -infinity to -1 that this graph is going to be concave up. Next we analyze the second interval. The second interval is from -1 to 1. Alright, obviously the best value to choose to substitute in is x equals 0. So we're going to substitute x equals 0 into the second derivative and evaluate it. When we do that, our f double prime of 0 is less than 0, which means it came out to be a negative number. So since the second derivative is negative on that interval, it tells me that the graph is going to be concave down from -1 to 1. Alright, then let's do the last interval. The last interval is going to be 1 to infinity. Alright, a logical choice for us to choose is x equals 2. You can choose something different. Alright, it's along that interval. Say you want to choose x equals 5, that's fine. But try to choose the easiest, most simplest, basic value to plug in there. So x equals 2, so we evaluate f double prime of 2. It comes out to be positive, right? F double prime of 2 is greater than 0. It's a positive value. That tells us that from that interval, from 1 to infinity, alright, the original function is going to be concave up. Okay, and we're going to start taking this to the next level too. Alright, and we're going to, be able to apply some different things and talk about extrema here shortly when we talk about the second derivative as well. But hopefully you guys all understand how we can analyze the second derivative and how it relates to us, what the concavity is of the original function. Alright, so if we take a look here at the graph of the original function, remember the original function is f of x equals 6 divided by x squared plus 3. And we can take a look at the concavity of the function here based on the intervals that we've calculated because of where the second derivative is 0. And we can see where the original graph is concave up, concave down, and concave up again. Okay? So, let's take a look at this part. Points of inflection. Alright? Points of inflection are important. Okay? There's 3 types of points of inflection that helps us determine concavity. Points of inflection tell us where concavities change. So we can either go from concave up to concave down, we can go from concave down to concave up, or we can go concave up, concave down, and you can kind of see where the tangent lines are applied. So one increasing, one's constant, one's completely vertical at the inflection point. So points of inflection help us determine where points of concavity change. That's really what you need to understand. Alright, so when we define what the point of inflection is, alright, by definition here it says let f be a function that is continuous on an open interval, and let c be a point in that interval. If the graph of f has a tangent line at this point c, f of c, then this point is called a point of inflection, which really means what? We are able to take the second derivative of the function at that point. Okay, we consider it a point of inflection. So that's where our concavity of f changes from either upward to downward or from downward to upward at that point of inflection. Okay, so very important. So how do we calculate points of inflection? Well, we've already kind of done it, but if we look at theorem 3.8, if f of c is a point of inflection of the graph of f, then either f double prime of c equals 0 or f double prime does not exist at x equals c. So this is very similar to what we did last section using the first derivative. What it's saying is a point of inflection is where either the second derivative is 0 or the second derivative does not exist. And you're going to be looking for that as we solve for points of inflection. So let's do this example here. We want to determine the points of inflection and discuss the concavity of the graph of f of x equals x to the 4th minus 4x cubed. Why we do this? Well, because your graphing calculator doesn't necessarily graph functions like this very well. For us to get a good understanding, you're going to spend a lot more time playing with your window and trying to see the actual changes and things like that. Okay, but for us to find the points of inflection, what we want to do is take the second derivative of this function. All right, so we can start by rewriting the original. All right, we're going to differentiate and find the first derivative. So the original function is x to the fourth minus 4x cubed. The first derivative is 4x cubed minus 12x squared. All right, and then our second derivative ends up being 12x squared minus 24x. And the best thing for us to do is factor that down, so we can factor out 12x. So we get 12x times x minus 2. And we're going to set both parts equal to 0. So we're going to say 12x equals 0 and x minus 2 equals 0. So our solution is going to be x equals 0 and x equals 2. So that's our two possible points of inflection. And remember, points of inflection are where we're talking about changing concavity, either from upward to downward or from downward to upward. The only way for us to really check with this right now is for us to determine, intervals on which this function is either positive or negative. So since these are our points of inflection, okay, we have 2 points of inflection, we're going to have 3 intervals. The first interval is going to be negative infinity to 0, the second interval is going to be 0 to 2, and the third interval is going to be 2 to infinity. And we're going to test values in there and substitute them into the second derivative and see if we can conclude if they come out positive or negative. And based on if they come out positive or negative, we're going to determine the concavity. So if we look at the first interval from negative infinity to 0, we're going to arbitrarily pick x equals negative 1 as a test point. It's a simple number and it's in that interval. So when we substitute negative 1 into the second derivative, okay, so f double prime of negative 1 ends up being positive, which tells us the graph on that part of the interval is going to be concave up. If we look at the next interval from 0 to 2, okay, we substitute in 1. It's perfectly in between. It's a great number to choose there. We're going to arbitrarily pick 1, so we're going to substitute in f double prime of 1. When we substitute that into the second derivative, all right, we get a negative value. So that tells us the graph is going to be concave down from 0 to 2. If we look at the third interval, 2 to infinity, we're going to arbitrarily test x equals 3. It's a good number to plug in there. So like I said, you can always, if you wanted to choose 10, you could choose 10 there. All right. But f double prime of 3, when you substitute that in, it ends up positive. Okay, so that we know, we can conclude that it's concave up on that interval. And we can see all this if we take a look at the graph on the right hand side. We can look and see where the points of inflection are. Okay, so the points of inflection tell us the difference or the change in concavity. So we can see from negative infinity to 0, the graph is concave up, just visually inspecting it. If we look from 0 to 2, we can see that the graph is concave down. All right, and if we look from 2 to infinity, we can see the original graph is concave up. Remember, everything about this second derivative test is telling us all the information we need to know about the original function. All right, so points of inflection, remember that happens when the second derivative is 0 or does not exist. Okay, so I just want you to think about that as we go through it. When we do this, though, it doesn't necessarily guarantee, all right, that the concavity changes. Okay, it's a possibility where the concavity changes. That's why you need to do your test intervals, because here's a graph. All right, if we take a look at this one, okay, the point of inflection is at 0, but if we notice, all right, the concavity from negative infinity to 0 is concave up, and from 0 to infinity is concave up. So even though there's an inflection point at 0, it doesn't necessarily mean that the concavity is going to go from upward to downward or downward to upward. It can, all right, and most likely that's where it's going to happen. But it doesn't mean that it holds true all the time. It is just a point of inflection, and it is where concavity could change. Not always changes. All right, so this is a case where it doesn't change, but we still have to find those points of inflection. All right, because it's going to help us, also find the relative max and mins if we want to. Okay, we used the first derivative test before in the last section. There's a way for us to use the second derivative to test this as well. Okay, so if we go through the second derivative test a little bit more, All right, f is concave down on an open interval containing c. If what? F prime of c is 0, then f of c must be a relative min or max, right? That's what we tested before. Okay? We tested before in section 1 when we knew the first derivative was 0, we had a relative max or min, right? Those were our critical points. Okay, where that would happen on the original function where we would have a maximum or a minimum. So that's kind of what we're talking about on the left there and how we can use both of these. So if we look at the graph on the left, right, it says if f prime of c is 0 and f double prime of c is greater than 0, then f of c is a relative min. Okay, so if the second derivative is greater than 0, okay, we're going to be concave what? Up and have a relative min. All right, if we look at the graph on the right, if f prime of c is 0 and f double prime of c is negative or less than 0, then f of c is a relative maximum, because remember f double prime of c tells us that we are concave down when it is negative or less than 0. Okay, so it's important that we write down all these rules and theorems. Alright, so let's look at theorem 3.9. We're going to look at the second derivative test. It says let f be a function such that f prime of c is 0 and the second derivative of f exists on an open interval containing c. So that's the important part. The second derivative does have to exist for this to hold true. Now, when we write this down, alright, it says if f double prime of c is greater than 0, then f has a relative minimum at c f of c. Alright, so what's that telling us? The second derivative, it's greater than 0, right? That tells us that we are concave up. Alright, anytime we're concave up, we're going to have a relative min. So that's really what that means there. If we look at the second part of that, when it says f double prime of c is less than 0, that tells us we are concave down. Anytime we have concavity down, we're going to create a maximum. So we will have a maximum at c f of c. Now, if the second derivative test fails, okay, it may have a relative max or a relative min, or neither, okay? If that fails, we go back to the first derivative test. Alright, so let's do an example here. We're going to find the extrema, right? Remember, extrema means we're looking for maxes and mins. Alright, using the second derivative test here. Alright, so we're going to work through this example. The original function here is f of x equals negative 3x to the fifth plus 5x cubed. Alright, so we got to start by taking the first derivative of this function, okay, and finding the critical numbers. So we can see that from the derivative, we can calculate the critical numbers are negative 1, 0, and 1, right? Because we set 15x squared equal to 0, and we set 1 minus x squared equal to 0, and we solve for x in both cases. So that's how we get negative 1, 0, and 1. That's using the first derivative test there to find the critical numbers, okay? Then if we take the second derivative, all right, of the function, we get negative 60x cubed plus 30x, okay? And when we simplify that out and factor out 30x, we get 30x times the quantity of 1 minus 2x squared. We set each one of those equal to 0. We're going to set 30x equal to 0 and 1 minus 2x squared equal to 0, okay? So when we do that, okay, it helps us create the points that we're looking for. Okay, so if we look at what happened, I'm going to step back just a slide here, just so we know, when we set 30x equal to 0, right, our value is going to be what? X has to be 0 for that case. So that's one of our points of inflection. Okay, and then when we set 1 minus 2x squared equal to 0, okay, that's going to give us a square root of plus or minus the square root of 1/2. So that'll be our other values that we're going to look at. Okay, so if we use the first derivative, we have negative 1, 0, 1. If we use the second derivative, we have 0, negative 1/2, positive 1/2. Okay, so we can take a look as we're going through here. Okay, and we have to create our test intervals. All right, so if we choose a test interval for our far left one, all right, that's going to be negative infinity to 1/2. All right, so f double prime of negative 1, we choose negative 1 there, is greater than 0, it's positive. So we know we're going to have a relative min. Okay, if f double prime of 0 equals 0, that test failed. All right, we didn't get a plus or minus value, right? We got 0 there, so that didn't tell us anything we needed to know on that interval. Okay, and then on the last interval, we have f double prime of 1 was less than 0, so we have a relative minimum. So the problem is, right, our second derivative test is failing, and you're like, well, why is it failing? Well, because we should get either a negative or positive value there. When we get f double prime of 0 there, we cannot determine if we're concave up, concave down. Okay, we cannot determine if there's a relative max or relative min that's going on there, because we need the sign change. And since there's no sign on 0, that's why that test is failing there. Okay, so since the second derivative test failed there, we're going to have to step back and take a look at the first derivative test as we go through this. Okay, so if we looked at that, and I'm not going to revisit how to do the first derivative test, we'd spend a whole section and things like that on it. You guys can take a look at that function. All right, we can clearly see that the original function is, concave up, okay, from negative infinity all the way to what, 1/2, right? Because that was our critical value. And then we couldn't tell what was going on from 1/2 to 0, or negative 1/2 to 0, and 0 to 1/2, right? Because if we look at this graph from a negative 1/2 to 0, it's concave down there. And then if we look at the graph from 0 to 1/2, right, it's concave up, and then from 1/2 to infinity, it's concave down. So we still have, it's harder on the visual eye here, but when we actually took the second derivative and found those critical values of points of inflection, at negative 1/2, 0, and 1/2, okay, very, very important there, so that we can visually inspect what's going on here to find maxes and mins and things like that. Alright guys, well that's the end of this lecture. If you have any questions, feel free to email me. Let me know if we need a team meet, Zoom meet, or anything else like that. Else guys, have a great day. I'll see you in class.